This is lesson number 1 on the fundamental counting principle and permutations and combinations. So first of all, the fundamental counting principle. Now, what we're looking at in the fundamental counting principle is if we have a number of choices, so let's say for stage A, we're looking at this model, the number of choices for the second stage, which we'll call B, and we're using this example up top here, so that's A, B, and this third stage is C. The number of choices for the third stage C, then if we're looking at how many ways we can have a particular task or option, so model 1 blue and model 1 in blue or red, then we say that we can multiply A by B by C by however many other options are available to us. So that's called the fundamental counting principle. So let's look at an example to kind of think about how this works. So if a toy manufacturer makes a wooden toy in 3 parts, so part 1, the top part may be colored red, white, blue, or pink, so there's 4 options there. And then part 2, we only have 3 options, orange, purple, and black. And part 3, we only have 2 options, yellow and green. There's 2 ways we can think about what this is going to look like. We can make a tree diagram, which is what they did up here. And so our first option was red, then we had white, then blue, and finally we had pink. Now each of these options had, so if I were to choose part 1, which is red, white, blue, or pink, then if I go with red part 1, then that red piece could then have an orange, purple, or black piece. So there's 3 options for each of these first categories. So orange, purple, and black. Now each of these categories had 2 options. They could either be yellow or green. That's the next combination of colors that we could have. And each one of these have the exact same options. And so if we were to add up, we would have yellow and green. And I'm just going to go Y or G, and I'm going to do the exact same thing. I'm just going to put the letters for each of these colors so it doesn't take too long here. So orange, purple, black, orange, purple, purple, black, orange, purple, black. And each of these, remember, have 2 options. And those 2 options for each of the second option was yellow and green. So if we're doing this these tree diagrams, you might notice that they get pretty convoluted pretty quickly. And so everything is pretty tight here. And so the fundamental counting principle is a lot more effective in determining how many different types of toys we can make using these various combinations. So if I were to count all these up, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, I could have 24 toys made up. But using the fundamental counting principle, we find that if I had 4 options the first time, and then 3 options the second time, followed by 2 more options, 4 times 3 is 12, times 2 is 24 toys, and we get the same result a lot quicker. All right, so that's the fundamental counting principle, where we take the number of tasks, so I have 3 different tasks, and the number of choices in each task, and I multiply those choices together. So I had 4 choices for the first task, or the first part. I had red, white, blue, or pink, and then the second task I had 3 choices, and the third task I had 2 choices. So that's where I get 4 times 3 times 2 from. All right, let's look at a few other examples. A math quiz consists of 8 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? Well, if I have 8 multiple choice questions, each question has 4 choices. That becomes 4 times 4 times 4 times 4 times 4 times 4. 1, 2, 3, 4, 5, 6, 7, 8 times 4. or 4 to the power of 8, and I get 65,536. So that's the number of answers that are available with this multiple choice test. Now, let's look at this next example. When solving problems involving restrictions, it is important that the restriction is dealt with first. And so let's look at this example below where we have to deal with the restriction. Eric has been assigned the task of determining how many odd 4-digit numbers there are. He's been told that a number such as 5,267 is a 4-digit number, whereas 267, which is starts with a 0, is classified as a 3-digit number. All right, so if it ends with a 0, then that's okay, but if it starts with a 0, that's only a 3-digit number. So the first step of his work is shown below, and explain his reasoning for using the number 5. Well, remember what we're looking for is odd 4-digit numbers. Now, why would he use the digit 5? Well, for a odd number, the last digit must be odd. And so if the last digit must be odd, then there are only 5 possibilities. We have 1, 3, 5, 7, and 9. So 1, 2, 3, 4, 5. There's only 5 choices for this last number, since it has to be odd to be an odd 4-digit number. And the second step of his work is shown below, and explains his reason for using the number 9. Well, we have to use the number 9 because we can use any number from 1 to 10, essentially, or 1 to 9, but because we can't use any number from 0 to 9, we can't use 0 at the beginning, because any number that begins with a 0 is considered a 3-digit number. So there's only 9 possibilities. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9, because we can't use 0. So that's why we put 9 there. Now complete his work to determine how many odd 4-digit numbers there are. Well, let's start with what he has. He has 9. We have those 2 filled in, or left blank. Now remember that if we're working with odd numbers, then this can be any number from 0 to 9, as can this one. It can be any number from 0 to 9. So there's actually 10 choices of numbers, because there's these ones, but this time down here we can include 0. So we can use 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of these are gonna work. And if we think about how many odd 4-digit numbers there are going to be, well, all we got to do is go 9 times 10, 90 times 10, 900 times 5, 4,500. All right, that's how many odd 4-digit numbers there are going to be. Now, the question's changing up a little bit. Eric has now been assigned the task of determining how many odd 4-digit numbers there are which have no repeating digits. So for example, if I had the number 8,113, yes, it's odd, but there are 2 repeating digits, and we can't have that. All right, so same with something like this, 1,117. That time we have 3 repeating digits, and we can't have that. We want no repeating digits. So explain why the first step in A is still valid. So in the first step in A, we had something like this, and in the second step, we can't use. So the last step, there are still 5 possibilities. Now we always want to start or deal with the restriction, so it has to be odd. So if it has to be odd, then obviously we can't end with an even number, so we can't end with 2, 4, 6, 8. And so there's still only 5 possibilities for the first numbers. Right? We still have 1, 3, 5, 7, and 9. So we still only have 5 choices for our first number. And the first digit still can't be 0, which means, 9 would be the logical choice, but it cannot be a repeat of the odd digit in the last position. So now that means that we can't use 1, 3, 5, 7, or 9 up here. So what that leaves us with is the numbers 10 minus 2, 8 possibilities for the first digit, right? Because if I can't use 1, 3, 5, 7, or 9, if I have other options, so if I make a list of the other numbers that I think 2, 4, 5, 6, 7, 8, 9, I count them 1, 2, 3, 4, 5, 6, 7, 8, 9, because 0 doesn't, or it won't be included, because if it starts with 0, then it's only a 3-digit number. Now, if I were to use one of these right away, that would only leave me with 8 left. So because I can't have a repeating digit, if I end with 1, I can't use 1 at the beginning. If I end with 3, I can't use 3 at the beginning. So that means that there are only going to be 8 choices. Now let's just use, let's say it was 1 as an example. That means I can't use 1 for my first number. So that would leave 1, 2, 3, 4, 5, 6, 7, 8 numbers. Now determine how many odd 4-digit numbers have no repeating digits. Well, same with the, it's going to be the same deal here, and if we have 8 to choose from, 1, 2, 3, 4, 5, 6, 7, 8, remember we can use 0, but if we used 1 earlier, then we can't use 1 again. And so this is still going to be 8 that we can choose from, because it can't be the first or the last digit. And this next one can't be the first, the last, or the second digit, so there's only going to be 7 numbers to choose from. And so if we multiply those up, 8 times 8 times 7 times 5, we're going to get 2,240. And sorry, I should have put that down here. Actually, all this work should have gone down there. All right, let's look at, we'll do example 4, example 5, I'm sure you can figure out yourself, and then we'll finish with example 6. So car number plates in an African country consists of a letter other than I or O followed by 3 digits, the first of which cannot be 0, followed by any 2 letters which are not repeated. How many different car numbers can be produced? Well, first of all, how many digits are there going to be? There's going to be 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Now, remember, the best way to go about these is to deal with the restriction first. So my restriction is, it can be any letter that does not consist of I or O followed by 3 digits. So that means that out of 26 letters, it can't be 2 of them. And the first letter cannot be 0. So from 1 to 9, there are 9 options. And then followed by any 2 letters which are not repeated. So next, I have 2 options to choose from. I have 10 and I have 10. Oh, sorry. The first of which cannot be 0, followed by any 2 letters. That's why I use 10 and 10. And they're not repeated. Or where we are, the first, followed by 3 digits, the first of which cannot be 0. There we go. And then followed by any 2 letters which are not repeated. And I have 26 options there. But since the second one cannot be a repeat, then there's only 25 letters that I can use here. And again, all we got to do is multiply these. 24 times 9 times 10 times 10 times 26 times 25. So 24 times 9 times 10 times 26 times 25. And I get an answer of 14,040,000. Alright, and so I don't want this video to be too long for you. Let's look at example number 7. So consider class example number 3, in which Eric was asked to determine how many odd 4-digit numbers there are. As an extension to his assignment, Eric has been asked to determine how many even 4-number digits there are, and how many even 4-digit numbers have no repeated digits. So let's first look at this option here. So determine the answer to I. Now, remember, if we are starting, we want 4 digits, and if we're starting with some sort of restrictions, then we always start with the restriction first. And with the restriction, there's only 5 options. Since if it's an even number, it can end in 0, it can end in 2, it can end in 4, 6, and 8. So there's 1, 2, 3, 4, 5 options for our last digit. But remember, for the first one, it can't start with a 0, so that leaves only 9 options. And then it doesn't say that in the first option, it doesn't say that we can't have repeats, so we have 10 and we have 10. And that will be the same as before. 9 times 10 times 10 times 5 will be 4,500. Now, Eric started his answer to part 2 below, where we have even 4 digits with no repeated digits, but he was not sure how to fill in the first space in his problem. Explain why he needs to consider 2 separate cases to solve the problem. Well, if the last digit, remember this time, is going to be 0, this time we can't have, and this time we can't have 0 as an option, right? And since we can't have 0 as an option for the first space, there's still 9 options available for this first space. So anything from 1 to 9. If the last digit is going to be 2, 4, 6, or 8, then the first space cannot be that digit. So there's actually 2 possible ways to do this question. So we're so explain why he needs to consider the 2 separate cases. So this is, we'll call this case 1 and we'll call this case 2. So if the last digit is 2, 4, 6, or 8, then the first space cannot be that digit, and it cannot be, we can't have a 0 with the other 8 possible choices. And so what we're going to have to do is we're going to have to think about, well, if the first one's not 0 because this one was 0, then there's actually only one option available. And I'll show you why in a sec. So if this is 0, this one won't be 0, obviously, so there'll be 9 choices, but that will only leave 8 choices here and 7 choices here. And in the second situation, I have 2, 4, 6, or 8, but I can't have any repeats of this, and I also can't have 0 here. And so this will, I'll only have 8 options to choose from, 1 to 9, excluding 2, 4, 6, or 8. And since this can be 0, but not the first number, this will still be 8. And since this can be 0, but not this number or this number, there would only be 7 options here. But because we can't have 0 here, because we use it up here, then there's actually only 4 options available in this choice here. And so that would leave us with 9 times 8 times 7 times 1, 504, and we'd be left with 1,792. But if we combine both of these choices, 1792 and 504, we are going to get 2,296.